Hello, my name is Diaz and welcome to my analysis and Simulink optimization of comparison between direct and reverse electroporation of cells in situ simulation study. So my article basically talked about models that analyze structural transformations to a cell membrane after the application of an electric pulse, making the cells permeable for a period of time. And this is really important for the study of potential cell therapy technologies, since we're able to introduce materials into the cell that would allow different purposes in this area of genetics. So yeah. So I decided to pick this article mainly because I wanted to apply the knowledge gained in this course to an internship I'm doing in cancer research. So I decided to analyze both direct and reverse electroporation. And direct electroporation is basically a transfection method that uses an electrical pulse to create temporary pores in cell membranes, allowing the transport of extracellular material like nucleic acids into a cell. So as you can see, the cell starts in this graphic above. The cell starts with intracellular and extracellular materials, and after a pulse is applied to the cell, this cell becomes partially permeable, allowing some of the material outside into the cell, and then it encapsulates again. So this is important because we could correlate the maximum voltage that we can apply to cells before killing them to get a feel of what the range of voltages would be to optimize this project, since we want to have a better yield of transfection but also have a good viability of cells, since we don't want to have excessively high voltages to kill our cells. So then basically this project focuses mostly on reverse electroporation and what changing parameters would be needed for this to be as effective as direct electroporation. And basically reverse electroporation consists of printing the nucleic acids on the substrate and then seed the cells on top of them, which is the opposite that normally happens, because direct electroporation first puts the molecules on top of the seeded cells. So it's basically just the order that's being changed and analyzed. So the equations and the models for this project were the ones as shown here that describe pore density creation, N of T, which describes induced creation of pores in the cell after the application of a high voltage for a short period of time. So you can see that it's dependent on cell radius, on creation rate coefficient, equilibrium pore density, and characteristic voltage of electroporation for the specific cell line, as well as pore creation rate. And the ITV is the induced transmembrane voltage, which can be described analytically as 3/2 times the electric field applied, times the radius of the cell, times the cosine of the angle between them. And for this experiment, the radius was assumed constant, but if a different cell population was analyzed, then this would be changed. The results that we end up having is that when an electric field of 1700 volts per centimeter are applied, it follows just as the results in the publication, and the cell ends up closing again after 10 seconds. When we apply an order of magnitude more of the electric field, the cells don't reseal completely. As you can see, they go to steady state at 150 seconds, but not at 0, so they will not reseal. And when comparing the results obtained with those from the original publication, both the results I got on the right with the publication results are the same. So that was a great accomplishment, and yeah, these are the references, and yeah, that was my project, and I hope to connect this further in the future.